Okay, the next topic is static condensation. Okay, this has some long linear algebra formulas, which you can stare at them and be happy, or you can work it out. Maybe there's not enough time in this tutorial to work out those formulas, but you know that they are there, and you can return to that whenever you want to. Static condensation refers to the process of eliminating unknowns that are inside an element and don't talk to other elements. Okay, so they are useful for standard methods, but some people here are experts in HCG method, and they are critical in HCG methods. Okay, so the purpose of this tutorial is to show you how to turn on the static condensation, and it's done by one keyword. The keyword argument is condense. Condense equals true or false. And then to understand what's happening behind the scenes, there is this long linear algebra formula, which has multiple pieces, and these pieces are all available in NGSolve as data attributes of a bilinear form. And these are the attributes: harmonic extension transpose, inner solve, and we'll see what all of that are in a second. And all of these help us do a Schur complement factorization of the inverse. And then we'll see how does NGSolve know to do this type of factorization. It needs to know the block partitioning, and the way that's implemented is using this data type called coupling type that divides an unknown in a finite element space into a category of local degrees of freedom or coupling degrees or not local degrees of freedom. And as usual, there is an automatic utility if you don't want to see all the steps, but you can call one-liner that'll do it for you. Okay, we start with the unit square again. Okay, this time we'll take the usual Poisson bilinear form and ask for condensation to be turned on by this keyword argument. Okay, so this is the one-line syntax where you assemble where you symbolically make the form and assemble it, and all of that happens at once. And here's the linear form, and we have a grid function. Okay, now we can think of this assembled matrix as block partitioned into local degrees of freedom and the remaining, which for this purposes we'll call E, or interface degrees of freedom. Okay, so we have the LL block, the LE block, and the other blocks. Okay. Just a block partitioning the matrix. So in the Lagrange finite element space, this E consists of edge and vertex degrees of freedom, whereas the L consists of the degrees of freedom that are interior to a triangle. So for example, in a cubic finite element, there's one degree of freedom that's interior to a triangle. And that'll be all of those, one per element will consist of this index L. Okay, and this is the Schur complement. You may have seen this from linear algebra. When condense is set to true, what happens is that the meaning of A dot assemble changes. A dot assemble does not produce the entire matrix A, but it produces this matrix with a lot of zeros and the Schur complement. Okay, so if you print out the A dot mat, expect to see S. And if you try to take the inverse of this, then you're not taking the inverse of A dot mat dot inverse, you're taking the inverse of the Schur complement of this matrix. So that this is, of course, there's zeros there, so you ignore the zeros and take the inverse of S, and it takes the inverse of S and pads it with the sufficient amount of zeros to get the same matrix size. And that's turned on by this flag. You look at Friedhoffs, and you pass into Friedhoffs only those degrees of freedom which are coupling degrees of freedom, the interface degrees of freedom, excluding the local degrees of freedom. Okay, so this statement does not take the inverse of the matrix A, but it takes the inverse of the Schur complement. Okay, how is that useful? Of course, we want to invert this matrix. The inverse of this matrix has this form. This is the factorization I was mentioning. It's a factorization into product of three matrices, and the inner matrix has this Schur complement inverse, which we made. So if we can make this and this and this, then we can implement this formula, and that's the static condensation formula. Okay, so how do we make these things? Well, these things are essentially provided to you. This matrix is provided to you inside the harmonic extension transpose. The other matrix, the one over here, is provided to you in harmonic extension data member, and this inverse is provided as the inner solve attribute of the form. Okay, so getting the full solution from the condensed system, therefore, is just a matter of implementing this formula. And here is a way to implement this in a newfangled operator notation that is now pervasive in NGSolve tutorials. In order to make, we're given this as the harmonic extension, and then we pad it with the identity matrix. That step is right here. This is the extension. The identity matrix plus the harmonic extension gives you this matrix. This thing is the harmonic extension transpose. Add to that the identity matrix, you get this matrix. And then you have to compose all of these three matrices together, and that's the operation here. It is this matrix composed with inverse of S without this component, composed with this, that's extension transpose, and then you add back this part that was left out, that's the inner solve. And that's the representation of the inverse of the matrix using this Schur complement factorization based on local degrees of freedom and interface degrees of freedom. And you can take that inverse and multiply it with the right hand side, and you get the solution. Okay, no questions? I can proceed. Yeah, question.
I was just going to note that looks like a lot of new things for the harmonic extension trans. The attributes have exploded recently, because I was hoping at one point to take the adjoint of one of them, and I couldn't do it previously, but now it's in here. That's really useful.
You can thank somebody.
Yeah, thank you for doing that. That's awesome. That's going to save me some of our code. Yeah.
All right.
I hope useful things are coming in then.
Because previously it had been kind of a C++ mystery somewhere. It's like, I don't know what this item is.
Yeah. Yeah, so some of the new things are built into the tutorial, so it's a way of disseminating the new things, and some other things are still remain secret now.
Well, you have to keep your secret.
Until the next user meeting, maybe.
There's always a decision what is made visible to the users and what is hidden in the PVP function. So I like to show it to people what is done behind the scene.
Yeah.
Of course, it needs some explanation and maybe.
Okay, so few more words of explanation before we quit this tutorial. In order to compute these things, it needs to the NGSolve needs to know what is L and E, which is this in this block partitioning. There were these index sets L and E, and the way it knows that, it's important to know the way it knows that because it's a unified framework for all finite element spaces, not just the Lagrange finite element space, and the implementation is using this coupling type. So if you take any finite element space, you can ask the finite element space to tell you the coupling type of every degree of freedom it has, and it's going to print out a whole list of things. And you see there is something called the wire basket degrees of freedom, etc., etc., and then interface degrees of freedom, etc., etc., and then local degrees of freedom. Okay, so we at least saw 3 different degrees of freedom types. I think maybe Christoph Lehrenfeld will talk about other types of coupling, right? Hidden degrees of freedom? No? Okay. Okay, that will remain hidden then. So in this example, we have three types of degrees of freedom: local, interface, and wire basket. And every finite element space in NGSolve has such degree of freedom classification. So if you are taking the source code and you're making a new finite element space implementation, you are required to provide this coupling type of each degrees of freedom. Okay. So what it's doing? So now that the what is marked local degrees of freedom is the index at L, and everything else is in E. In our previous formula, that's how the factorization is implemented when condense option is turned on. And so you could do condense on any bilinear form on any finite element space as long as you have arranged things so that this block ALL is invertible and the Schur complement is invertible. Okay, now here's things get complicated when you mix the Dirichlet boundary condition stuff in the previous tutorial with the static condensation, and so this is just there for your reading pleasure because I'm not going to explain this. And you will stare at this very nice terse little code and wonder what is happening here, and then after some minutes you will realize that it is the correct expected thing to do. But okay. And then there is the automatic facility where if you don't want to think, you just want to solve the problem, get it done, and you just call the solvers module and do BVP and provide it with the bilinear form, linear form, etc., and out pops the same solution. Okay, it's printing out the error just to check that we've got. In this problem, the error should be machine 0 because the exact solution is in the finite element space. Questions?
Sorry, I'm asking a question after every single one, but is it fair to say like a wire basket DOF is like kind of like a vertex degree of freedom is shared between more than two elements?
In the Lagrange finite element space, that's a good way to think about it. We'll see another. We can actually tweak wire basket degrees of freedom by redefining the coupling degrees. So you might say I want the edge to be a wire basket but it's
fair to think of this like
yeah.
It's not always the case, but
yeah,
in the summer case it is.
It'll come back in maybe in the 2.1 or something. We'll see that again. Other questions? All right.